So experience shows that it's an extremely bad idea to give a mission critical lecture on the Friday before spring break, so I'm not going to do that. I thought that what I would do instead is talk to you about some of the work that I did during my graduate time here. And in particular, I thought I would just give you my PhD dissertation defense. And I'm doing this for a few reasons. One is that it's microcontroller related, and so given that you're all in a microcontrollers class, perhaps you'll find it kind of interesting. The other reason that I'm doing it is because I did this here in the Space Systems Design Studio over in mechanical engineering. Some of you may have participated as undergraduate researchers in that lab and actually continued to work on this kind of stuff, and so it might be kind of interesting to see where some of this started. You've now since improved upon it. This is 5 years old at this point, and so some of it's actually a little bit dated. And then the other reason I thought this might be worthwhile doing is some of you might be thinking about doing a PhD. And if you are, I'd be happy to talk about sort of the pros and cons of doing that kind of thing. But if you are thinking about that, perhaps it's interesting or useful to see what a PhD in this kind of thing could look like, with the understanding that they always look very different. So this would be an example of what a defense in this kind of field could look like. And maybe before I get started, I can let you know the context in which a presentation like this is given. This would be given at what this university calls your B exam, which is your dissertation defense. And the way that a presentation like this works is it begins with the presentation that I'm about to give you. And this is a public presentation. And so everybody's invited. And in fact, if you pay attention to the listservs, you may get notified when such presentations are taking place. They're really interesting to go attend. And the public aspect of them are meant to be public, and so it's not generally super duper crazy technical. These sorts of presentations are supposed to be for slightly more general audience, and so you can go and get something out of them. And so the whole dissertation defense begins with that presentation, and during that presentation, the only people that are allowed to interrupt the presentation are the members of the candidates committee, which is generally 3 or 4 professors. And as they're talking, those people will be interrupting constantly to ask questions and ask for clarifications and to probe a little bit. After the presentation, the audience is invited to ask questions for 15 or 20 minutes or so, after which all of the audience is supposed to leave, and the only people that remain in the room are the person that gave the presentation and the 3 or 4 professors on the committee. Then for a subsequent 90 minutes or so, you get grilled. And they poke and poke and poke and poke at you. After having done that, then the person giving the presentation, the candidate, leaves the room and sweats it out in the hallway. And the committee members sit there and decide among themselves whether or not they're going to give that person a PhD. They make that decision and call the person back in and generally shake your hand and say, congratulations. And then that's the end of that. So that's the context under which such a presentation would be given. And if you go to one of these, what the person is supposed to articulate in these presentations, the idea of doing a PhD is your goal is to make a contribution to your field of study. And it's going to be a really narrow contribution. But you're supposed to advance the state of the art in some domain, some way. The idea of a dissertation defense is to, as clearly as the candidate can, articulate, here's what I'm arguing my contributions were over the past 4 or 5 or 8 or 10 years or whatever it was. Here's what I've been working on, here's what I've learned, and I've pushed the state of the art in this very narrow domain in the following ways. And they're supposed to articulate that as clearly as they can, and then the whole rest of the presentation is their defense of those contributions. It's their explanation of, here's what I learned, here's what I did, here's, how I can prove that I have made those contributions. So if you go to one of these, this is what you'll likely see. So with that said, I'm just going to go through this. I may not get through all these slides, and that's perfectly okay. And you can please feel free if you want to interrupt me at any point if you want to ask questions or anything about this. This is a rare this is something that actually many of you might know quite a lot about, like I said, depending on if you've been doing undergraduate research in Space Systems Design Studio. So the contributions that I will defend in this presentation include the articulation of a field of study within aerospace engineering that relates to these new flavors of spacecraft that I'll talk a lot about. And called these R-selected spacecraft for reasons that I'll get into. The second contribution is an advancement of the state of the art for that particular technology, this particular flavor of spacecraft, making it better in some measurable ways. An algorithm that describes how you can move information optimally through a large swarm of these satellites. As I'll talk about, one of the advantages of these very tiny satellites is you can carry them to orbit by the hundreds or thousands or millions and deploy them all. How do you move data through a collection like that? And so I spent some time studying that. Made some efforts to try to translate some of this research that was being conducted originally for spacecraft applications to more terrestrial applications. So using the spacecraft, as I'll describe here in a moment, for some digital agriculture purposes. Instead of putting them in orbit, putting them in vineyards and orchards and on cows and using them to help facilitate those kinds of things. And then early on, I won't talk much about this, but an algorithm that allows for a spacecraft to navigate in cislunar space, that is to say the space in the vicinity of Earth and Moon, by using cameras to look at the sizes and phases and relative orientations of the Earth and Sun and Moon. You can kind of triangulate where you are based on that. So those are the contributions that I'll defend, but the questions that I really hope to try to clarify and answer, the ones that I really care about trying to make clear are, first of all, what are chipsats, these little satellites? It's kind of an interesting, newish technology, so what are they? Why are they interesting and what are they good for? And so I hope that after the presentation, people will have some understanding of the answers to these questions. So let's start with the first. What is a chipsat? Well, it's a very tiny spacecraft. Essentially, it's a printed circuit board where every item on that printed circuit board is chosen, among other things, for its robustness to surviving in the space environment. So each chipsat, each little spacecraft, is designed as a free-flying spacecraft. Each has a processor and a suite of sensors and a radio. They use their sensors to take measurements, and then they use the processor and the radio to communicate those measurements to one another in a network, and then back down to data aggregating receiver stations. And an obvious point, but these little spacecraft, this is 5 centimeters on a side, they're very different than conventional spacecraft. They're different in some ways that are rather obvious and in some other ways that are more subtle. But all of these differences, I would argue, boil down to one fundamental observation that makes them very different from a conventional satellite. And that observation is that an individual chipsat is effectively useless. The thing that's useful is a large collection of these things. If you consider an individual chipsat, the data rate that you get out of one of these things is really low. So low that it would be really hard to do like meaningful science with that as your scientific measurement tool. But the data rate that you get from a large collective starts to be competitive with the data rate that you get from a conventional satellite. Right? So the observation here is, if the definition of a spacecraft is a machine that does something useful in space, then the spacecraft is not the individual chipsat. The spacecraft is the collection. This is the spacecraft, not the collection. And so, you can then ask yourself, if this is the spacecraft, what are the open research questions associated with this kind of satellite? And this is a non-exhaustive list, but the open research question include questions like the following. They're questions like, how do you move data among a collection of chip satellites? How do you send commands to a very large distributed swarm of spacecraft? How do you actually send commands to it? If you do send a command to it, how do you execute a maneuver? What does a maneuver even mean in this context with a large disaggregated swarm of these things? How do you control their orientation? How do you plan missions with these things? How do you talk about mission assurance? That is to say, the statistics of probability of mission success. There's a lot of questions. That's a non-exhaustive list, but there's two really interesting things about this collection of questions. One of the interesting things about them is that there's just a lot of them, so that's kind of interesting in its own right. But the other interesting observation is that questions like this have been basically answered for conventional satellites since like the late 50s, early 60s. We've known for a long time how you send commands to a conventional satellite. And so there's something very different about these swarms of chipsats that are bringing us back to a very, very fundamental set of questions about a technology in space. And so my contention is that this is a clue, that the nature of these research questions indicates that these chipsats and these swarms of them do not represent some incremental improvement upon existing spacecraft technology, but that instead they should be thought about as a very different kind of tool. As I'll explain, they don't replace conventional satellites. They aren't useful for the same set of applications. But the fact that the open questions about how to use and operate these things are so fundamental suggests that it's kind of a different thing than a conventional satellite. And that difference, I think, is actually best articulated in the language of ecologists. This is where that R-selected choice of vocabulary comes from. Some of you may remember from like a high school biology or ecology class this concept of R selection and K selection. And if you don't, I'll just remind you. This describes essentially nature's two solutions to the problem that every organism has to solve. And the problem that every organism has to solve is making sure that enough offspring survive to reproduce in the next generation to perpetuate that species. And this falls into two broad, I'm going to talk about this as two solutions. It's really kind of a spectrum, but we can think about this in sort of two different ways. One solution that nature has arrived to solving this problem is K selection. This is the solution that we use as humans. It's the solution that's also deployed by whales and elephants and kangaroos and penguins and a gajillion other animals. And the solution here is you produce relatively few offspring in your lifetime, and you devote a huge amount of time and energy, and in our case money, to trying to make sure that these offspring survive and are successful into adulthood. This, as evidenced by our own existence and by the existence of so many animals that deploy this technique, works really, really well. But it's not the only solution that works really well. The other solution that you see among another huge collection of organisms is R selection. The solution here is rather than producing few offspring and devoting a huge amount of energy to each of them, you produce tons of offspring and devote almost no energy to any of them. So this is the solution that's deployed by things like rabbits and other rodents, by octopus and sea turtles and a whole bunch of other animals. The sea turtle, in some evolutionary sense, understands that the probability of success for a single egg is about 1 in 1,000. So it's a rough life being a young sea turtle. But she kind of is okay with that and says, okay, well, I'll just embrace these statistics of failure and lay 5,000 eggs in my life, right? And so you overwhelm the probability of failure with just a huge amount of numbers. And the analogy is probably obvious at this point, but we have a very similar problem to solve in spacecraft engineering. We have to make sure enough spacecraft survive to accomplish the mission. And I was speaking to the fact that this set of open research questions associated with chipsats indicates some fundamental difference. I think this is that fundamental difference. I think every conventional spacecraft to date has been K-selected, which is to say, a spacecraft engineer produces relatively few spacecraft in their lifetime. It's not uncommon at all for an engineer in this field to devote their entire career to a single spacecraft. That's very common. And you spend a huge amount of time and energy and money trying to maximize the likelihood of success for that spacecraft. Think like Hubble, Cassini, these big NASA flagship missions, James Webb. A huge amount of effort goes into trying to maximize success for that thing. And that's part of the reason that they're so expensive. I'd argue that chipsats are perhaps the first example of an R-selected spacecraft. The idea here, just like the sea turtle, is we understand that the probability of failure for an individual chipsat is really high, at least as compared to a conventional spacecraft. The likelihood that this thing fails is probably a lot greater than the likelihood that James Webb fails, for instance. But that's okay because these are so small and so low cost and so low mass that we'll just carry them to orbit by the hundreds of thousands. And if 50% of them die, that's fine, right? So as long as we understand the statistics of failure, we can do the back of the envelope calculations to say, okay, if mission success requires that I have X number of chipsats alive after Y number of days, and if I have a certain probability of failure per day, we can solve for the amount that we need to launch. And it might be a huge number, and in the case of chipsats, that's okay. And I'll just mention incidentally that I believe that the reason that we haven't seen this kind of solution to mission assurance previously is that it hasn't really been possible until relatively recently. In order to deploy this kind of solution to spacecraft mission assurance, you need to be able to manufacture your spacecraft for next to nothing, right? You need to be able to manufacture these things for dollars or pennies. They need to be really low mass. You know, they need to be able to communicate with them over long distances. And until really the big commercial electronics boom that made the kinds of manufacturing processes that you require to make these things so inexpensive, it was impossible to make something with those properties. So I think now, thanks largely to the cell phone industry and a few others, this is sort of a viable solution. But I think that's why we haven't seen it earlier. And so just to summarize, I think this is why that set of research questions is so fundamental. I don't think that these chipsets represent some incremental improvement on existing technology, but are instead something different. They're a different tool. And so it raises this question of, you know, if you think about the evolutionary history of, say, small spacecraft, which perhaps started with Sputnik, and then you have Explorer 1, and so on and so on and so on. Maybe CubeSats are the latest example of a small satellite. Would it be appropriate to put a chipsat after the CubeSats? And I don't think it is. I think this suggests two things that are a little bit incorrect. I think it suggests, first of all, that an individual chipsat is useful, which is not. Like I said, it's the collective that's useful. And furthermore, it suggests that the fundamental innovation here is in a reduction of mass. I don't think that's true either. I think the innovation is not in a reduction of mass, because in order to do something useful in space with these things, you need to launch so many of them that the swarm mass is, you know, perhaps approximately the same as a single conventional satellite's mass. So I think the innovation is not a reduction of mass, but instead a fractionation of it. You split the spacecraft into perhaps a million different pieces and distribute it. I think that's the innovation. So I don't think that's quite right. And so where do you put this? And I don't know exactly, but I think it breaks off and is kind of its own different evolutionary path, I think, with, you know, perhaps the most recent common ancestor between chipsat swarms and conventional satellites is, maybe it's not Sputnik, but it's something early on. That would be the claim. And it's worth clarifying that, you know, as with anything, this kind of work does not occur in a vacuum, and I'm far from the first person to think about chipsats or from small spacecraft. This is a collection of some of the publications related to chipsats, and I'm just indicating that I'm contributing to a train of thought that's been occurring for a long time. Okay. So that I would say would be a defensive contribution one. Contribution two would be an advancement of the state of the art of chipsats. That is to say, this chipsat technology, making it better, to making a new version of it that has some new properties that make them a little bit better. And I'll start by just giving you a little bit of history of the technology associated with this, of this kind of technology. This chipsat-related work began in 2010. And in fact, folks were thinking about it before 2010, but before 2010, people were mostly thinking about, could we make a spacecraft on a single piece of silicon? And actually, the people are starting to return to that thought now that that seems to be becoming more viable. But we're thinking about it earlier than that as single pieces of silicon. And then PCBs became kind of really easy to make and manufacture. And so it pivoted a little bit towards, okay, let's try a spacecraft on a printed circuit board. The first example of that was in 2010. Zach there is Zach Manchester. He was a graduate student in my research group, sort of the generation before me. He's now a faculty member at Carnegie Mellon. But he made these very simple little, well, simple, nothing simple. But he made these little printed circuit boards that essentially just had a radio beacon on them. They were taken up to the International Space Station and put on the outside of them, on the outside of the space station, exposed to space. And this was a simple experiment. The experiment was just how well do these commercial electronic components do in the stresses of space, exposed to the thermal fluctuations and the radiation and everything else. And so they were stuck out on the outside for, I can't even remember how long, maybe a year, and then brought back inside by an astronaut, put back down in the capsule. They came back to the lab, booted them up, and they all still worked, right? Which does not mean that they will always all still work, but it suggests that there's a non-zero probability of success, which is interesting. And in 2013 was the Kicksat-1 mission. Kicksat-1 carried about 100 of this iteration of the chipsats up to orbit and deployed them. And you could think about this iteration of the chipsats as being essentially the chipsat version of Sputnik. All that they were programmed to do was broadcast out a radio beacon, and the goal was just hear that beacon. Because it was not obvious that you could necessarily receive radio transmissions from something so low power over such long range. The exercise was to demonstrate that and to prove that concept. And in fact, it's called Kicksat because this spacecraft was the first that was fully funded on Kickstarter. And so in fact, the messages that were being beaconed were the initials of Kicksat contributors. And so many of these were ham radio people, and so they could go outside with their ham radio equipment and try to listen for their chipsat. 2016, I would say, would be my first contribution to this sort of lineage. The modifications here included, this was a 2-layer PCB, that became a 4-layer PCB. Embedded within the inner 2 layers there are loops of wire through which we can, by way of a H-bridge motor driver, move current this way or move current this way. You put current through a loop, make a little electromagnet, right? And so the addition of these torque coils allows for us to generate a magnetic moment in space that interacts with the Earth's magnetic field and causes a torque. And so that gives us the ability to do a little bit of orientation control of these things. Essentially, you deploy them spinning, you generate a magnetic field, you feel a torque by the Earth's magnetic field, and you can make it precess about the Earth's magnetic field. So you can kind of reorient them. And a few other additions that I'll just kind of gloss over at the moment. But the one that I spent the bulk of my time really working on, and the one that I want to talk through the technical details of, is this chipsat here. This was how I spent most of my time. It's a chipsat that I affectionately call a Monarch. Why call it a Monarch? Well, it's small and it's orange, kind of like the butterfly. And you may be aware that monarch butterflies do this fascinating thing where they migrate as huge swarms down to the Sierra Madre Mountains in Mexico, and they aggregate in these tremendous numbers. And that seemed vaguely spiritually connected to what these things do, which is migrate in huge swarms across, through orbit. And furthermore, if any of you have spent any time or done any internships in the aerospace industry, you know that it is an industry absolutely filled with highly cryptic acronyms. And I think that's very dumb. And so I wanted just a nice name. And so it's just called a Monarch for that reason. And I did draw that picture. Yeah, very proud of that. So it's different from its predecessors in a few ways. One is that it's actually got a little bit of a bigger surface area. The chipsat before this one was 3.5 by 3.5 centimeters. The Monarch's 5 by 5 centimeters. Which feels a little bit like a step in the wrong direction. Our whole exercise has been trying to make these things smaller and smaller and smaller. And so we made this one actually a little bit bigger, though as I'll explain in a moment, it's actually about 1/4 the mass of the old one because we made it out of a different substrate. This is Kapton, polyamide Kapton, as opposed to FR4. But the reason that we made these a little bit bigger was to accommodate these solar cells from a company called Alta Devices, which I don't believe is actually around anymore. They've been subsumed by some other company. But these solar cells produce 300 milliwatts each, which doesn't sound like much, but the previous iteration that included these solar cells, these were 40 milliwatts each. And so it was a tremendous power boost. It cost us a little bit of extra surface area, but for that much extra power, it was worth it. And like I said, you still have smaller mass, so it's still not necessarily a step in the wrong direction. But with that extra power, we suddenly had the power budget to accommodate some really interesting sensors. The most interesting one of which I think is a GPS module. So each of these Monarchs carries on it a GPS chip, a little GPS chip antenna, and an LED that indicates whether or not it has a fix. What makes this so exciting is we deploy these things in low Earth orbit, that is to say beneath the GPS constellation. And so GPS actually works where these things are flying. And a lot of the most interesting scientific experiments that you might want to do with these things require that you know where you are when you gathered some other measurement with your other sensor. And suddenly with the GPS, we know where these things are, which is really, really enables really interesting science. For instance, you could imagine deploying these things at the top of the atmosphere and just studying how they fall. The atmosphere is this crazy vector field with stuff moving all over the place. People often study the atmosphere by way of weather balloons, which tells you something, but it's one data point in this massive vector field. Wouldn't it be interesting to have sensors just being moved around by this vector field as they fall so that you could study, all the different arrows pointing all the different directions? And you can come up with a bunch of other examples where it's really handy to know where these things are. So the ability to accommodate a GPS was really exciting. It has some other sensors as well. It includes a radio that I can talk about, but rather than using an external dipole antenna, which the previous iterations used, we chose here instead to use an embedded PCB antenna. The thought here, the performance of this antenna was not as good as the external dipole. The gain of it wasn't quite as high. But this allowed for us to procure these things from the PCB manufacturer ready to go. There was no extra step associated with having to put on antennas. And so in bulk, it made these much less costly to manufacture in very, very large numbers because it removes a bottleneck from the manufacturing process. And so though the performance is a little bit lower, it was worth it to get the extra manufacturability. There's a little coax there to tune these things by way of a vector network analyzer. I spent a couple weeks doing that. Each of these carries a CC430 microcontroller, chosen for a couple reasons. Or I'm sorry, not a CC430, a CC1310. One of the reasons that I chose this microcontroller is it's very low power, sort of designed as a low power microcontroller. So when you put this into a low power mode, it's a really low power mode, and that's handy. It also has a built-in CC1101 radio. And so there is no external radio chip here. The radio is built into that CC1310 microcontroller. And all the embedded software here uses Texas Instruments TI RTOS, their real-time operating system. This was a dumb idea. I later replaced this, but I made the observation that, HDMI plugs have like 19 pins. That seems like I could break out a huge amount of I/O through if I cut a HDMI cord, and then I can break out all these pins. It turns out that the characteristics of the wires there made it very challenging to program this via JTAG, which is how I wanted to program this. So in subsequent iterations, I replaced this with a more conventional JTAG connector. That just caused me a bunch of headaches. Each of these is 4 layers, and like I said, inside there's these loops of wire through which we can drive current to generate a magnetic moment, to generate a torque, to turn these things a little bit. There's a little motor driver here for controlling the current in one direction or another direction. There's also, in parallel with that, a full bridge rectifier, which means we can wirelessly power these things. You can put it above an inductive charger, essentially, and they boot up. That was exciting because one of our goals for these was to have a bank of them in the space station, unprogrammed, so that if something interesting happened in space, say the sun did some interesting thing, you wanted to deploy like a heliophysics experiment, you would have essentially on-call spacecraft that you could program for whatever specific interesting phenomena it is that you want to respond to. And so the thought is that these would be stored in basically their motherships on shelves. We could wirelessly power them through their little slots, if there were little loops of wire that they were next to, program them wirelessly, and then deploy them. Each also includes an ambient light sensor. That's exactly the same sensor that when you open your laptop and it dims to the brightness of the room, it's that kind of a sensor. And then each has an IMU, an accelerometer, a gyroscope. This one also has a magnetometer built in. Ambient light sensor on the front and the back. And it's made of this really interesting Kapton substrate. So like I said, it's though it's larger surface area, it's actually lower mass. So that's a summary of all the hardware and its capabilities, which I've spoken to. Is there anything here to mention? Not really. Oops. Okay. So there's a demonstration video that I won't play, but it just exercises all these features. So I mentioned at the beginning of this that I was hoping to explain what chipsats are, what makes them interesting, and what they're good for. And so I'd like to talk a little bit about what they're good for. And to my mind, this kind of a spacecraft, this big, massive swarm, is useful for two broad categories of mission. One of those categories is for distributed sensing and monitoring missions, where you want to spread these things out over some big area and gather measurements from that whole area, right, and sort of route them back to a data aggregating station or something. The other flavor of mission that these are really useful for is missions that pose really high risk to individual chipsats. Because like I spoke to earlier, we can sort of embrace the statistics of failure here. They're so easy and cheap to manufacture that if you could do a mission where, the likelihood of failure for any individual chipsat might be 90%. Maybe you're just shooting them at the moon, right? 90% are going to fail on impact. But that's kind of okay, right? You can just figure out how many you need to shoot at the moon, and you launch that many. I want to talk a little bit about each of these. I'll start first with these distributed sensing and monitoring missions. So you could imagine, for instance, carrying a large collection of these to orbit and deploying them. And it turns out that if you deploy all these things from a mothership, they end up sort of stringing themselves out along an orbit. And the question is, how do you move data? Let's see, is this a video? Yeah, so you can imagine, this is an exaggerated view. But this is approximately what happens when you deploy these things. They stay largely coplanar, but with their slightly different initial velocities when they get kicked out, over an amount of time, they end up stringing themselves out. The little star there is supposed to represent a little ground station on a rotating Earth. And so the question is, if you find yourself in this kind of a situation where you've carried a whole bunch of these things up, you deploy them in orbit, and now they're sort of distributed in a ring around the Earth, how do you move data through this collection back down to, say, a ground station? And I want to make just an observation. The observation that I'd like to just gently make is, I keep making this claim that I think these represent something different, a different tool for space, very different from conventional satellites. One of those differences, I think, is reflected in how you represent these systems mathematically. If you have a conventional satellite, like a Cassini, or one of the NASA flagships, New Horizons, or whatever it is, when you're thinking about where that spacecraft is as a function of time, you're going to be using differential equations. Because if that thing costs $1 billion, my God, do you care where it is and how it's moving, right? And so that is to say that if you're modeling the location in space of a conventional spacecraft, you're using equations kind of sort of like this, right? Differential equations. But I would contend that with these chipsats, you don't really care about the individual position of an individual satellite as a function of time. What you care about much more is the distribution of the satellites. Where are most of them most of the time? And so that is to say, we're sort of out of the world of differential equations and perhaps more into the world of probability density functions. You're modeling your swarm as a probability density function, so that you're thinking not about where the individual constituents are, but instead where groups of them tend to spend their time. And so, like I said, the question is, how do we move data through this thing? And if you're going to come up with something like a routing policy, you need to decide upon what information is reasonable and unreasonable to assume an individual chipsat has access to. And people might have different sort of assumptions for this. You could debate whether this is exactly right, but the way that I thought about this, I thought it was reasonable to assume that each chipsat knows its own position and velocity, because it has a GPS. We're going to assume it's beneath the GPS satellite, so we can use that. We're going to assume that it knows the angular rate of the Earth, because that's just a parameter. And I'm going to furthermore assume that it can measure elapsed time. Not necessarily absolute, well, I guess with GPS you could measure absolute time, but in short, it knows how long it's been deployed. It can increment a timer. What does it not know? I'm going to assume that it does not know the number of nodes in the network, because chipsats are dying all the time. We may be replenishing them asynchronously, and it doesn't know exactly how many other chipsats there are. It doesn't know the topology of the network, because the neighbors are changing all the time, right? So there's no fixed neighbor for an individual chipsat. It's always changing. I could imagine situations where they might actually know this information, but for purposes of this exercise, I assumed that they did not know the locations of the ground station. That is to say, you could walk out into your backyard anywhere on Earth and pop up a ground station, And I want a routing policy that gets the information to you, wherever you may be, in a very efficient way. And I assume that they don't know the position of any other nodes in the network, again, because it doesn't scale, right? So they only know about themselves, really. And you can frame a problem, like let's say we have some node up there with some information that we want to get to a ground station here. That node doesn't know how many other nodes there are. Its neighbors are changing all the time. It doesn't know where this ground station is. And so as it moves, it's faced with a series of decisions. It will pass within a communicable distance to some other chipsat, and it needs to decide, is it a better idea for me to hold on to my data, because I think I'm going to get to this ground station, wherever it may be, first, or is it a better idea for me to relinquish my data to this other chipsat, because I think probably it will get to the ground station first. You can frame this as a series of optimal stopping problems, for which there exists, a mathematical infrastructure that you can turn the crank of. Most famous example of like an optimal stopping problem is the, people talk about this as like the marriage problem. This is the way it's always introduced, where if you imagine that you are going to date n number of people, and you happen to know what n is, which of course none of us do, an optimal stopping problem is, at what point should I stop and get married? And so you can frame these kinds of problems this way. It's a very analogous problem here. This chipsat, it's moving in the direction of the ground station. It doesn't know when it's going to get there. It's encountering these other chipsats on the way. At what point should it relinquish its data? Or should it ever relinquish its data? So you can turn this crank, and this is just a few videos of, you can only play one at once. They're a little bit hard to watch, but if you keep an eye on the star, you can watch this thing making its decisions about whether or not to relinquish data. There it gave it up to that one, gave it up to that one. It doesn't always make the right decision because it doesn't, have global knowledge. So in that case, it actually made an incorrect decision. But it's generally making decisions that minimize the expected time to the ground station. And each of these decisions is informed by those two chipsats exchanging with each other only the information that they actually have. Where it is, its timer information, and really that's it. And they're using that to figure out, who's on the trajectory that's going to move me forward fastest, basically. I'll just mention as a total aside, to my absolute delight, I've developed something of a professional relationship with some folks that are delightfully wacky folks that are really interested in searching for Dyson spheres. Do people know what Dyson spheres are? These are hypothesized extraterrestrial mega engineering structures. They are structures that you would build to extract all of the energy of a star. And so you'd completely surround the star with an engineered system so that all of the energy coming out of the star gets absorbed by your mega engineering structure to deploy on, I don't know, whatever that civilization wants to use it for. And so this group of people is asking, if these things did exist, how observable are they? Could we look for them? This person I've been interacting with thinks that they might become infrared emitters. So deploying, acquiring time on space telescopes to look for anomalous IR emitters, thinking, well, perhaps that's a Dyson sphere. But the observation is that such a sphere would probably be composed of a whole bunch of disaggregated stuff. Can show that physically a contiguous structure is not stable. So it's probably a bunch of disaggregated stuff. And so to my absolute delight, some of this stuff has become relevant to the search for Dyson spheres, which is awesome. I'm going to a conference in June called Dyson Minds that hypothesizes a Dyson sphere devoted to compute. What if you could build a computer that used all the energy of a star? What might that computer be capable of? If an AI were running on that computer, what would it be thinking about? What algorithms would it be running? So just, I don't know, fun stuff to think about. Just mention my personal take on this is I think maybe a sufficiently advanced computer becomes indistinguishable from nature. Maybe a Dyson mind doesn't surround a star. Maybe a Dyson mind looks like a star. You look at it, looks like a star just doing star stuff, but in fact, perhaps that whole thing is a computer. Maybe. I have a lecture related to this that if you'll indulge me at the end of the semester, I'll give. I think the whole world's a computer. That's just me. The other class of missions for which I think chipsats are really well suited would be those that pose really high risk to individual chipsats. A great example of these would be those that involve entry, descent, and landing onto other celestial bodies, for instance, the moon. Many of you are aware that for the Mars rovers, for instance, the most dangerous part of that mission is getting from orbit to the surface, because you have to dissipate kilometers per second of energy relative to the planet, to zero motion relative to the planet in about 7 minutes through an atmosphere. Yeah, it's a thin atmosphere, but that actually makes the problem a little bit more challenging, as it turns out. There's not enough atmosphere to be useful necessarily for parachutes, not that useful. Deploy a parachute and you're still screaming towards the ground at like 700 miles an hour. But there's enough atmosphere to heat you up. So it's a really hard problem. The chipsat approach to this problem, the R-selected approach to this problem is forget about it. Just shotgun these things at the surface and, figure out here on Earth by doing some experiments what fraction of them you expect to survive impact and what fraction you expect to die on impact. If you find that 95% of them are going to die on impact, okay, just shoot that many more at the surface of the celestial body. But the question is, would they survive impact? Because of course, if the probability of surviving impact is 0, then this doesn't work. And so I conducted an experiment with some collaborators at the University of Maryland, and actually in collaboration with this interesting company called New Ascent, who is trying to replace the first stage of rockets with a huge Jules Verne-style gun. So you just bang, shoot your satellite up towards space, and then turn on only a second stage engine. Just delightful. But these folks at University of Maryland have a really huge drop table. So you can imagine this being a piece of test infrastructure that includes a platform, basically with big rubber bands holding it to the ground. You crank this thing up and let it go, and it slams into the ground. Of course, it's more sophisticated than that, but that's the basic operating principle. So you can slam stuff into other stuff at up to 27,000 Gs. And so the experiment that we conducted in collaboration with these folks is to get some lunar regolith simulant. This is stuff generated by NASA Ames to be very, very much like moon dust. It has the same properties of moon rocks and dust. And make a little bed of it, and then slam chipsats down onto them at up to 27,000 Gs. That's about the order of magnitude that you'd expect, just crashing into the moon. And this was a really simple experiment. All that we were asking is, after we do this, is it still working? Like, characterize all the sensors before doing this, make sure they're operating to within their datasheet specifications, do the same thing after. Did any of them degrade or break or anything like that? And to our surprise and delight, all the sensors continued to operate just fine. This is some data out of the IMU before and after being slammed at 27,000 Gs. The IMU is still operating just fine. And so again, what this does not indicate, that every chipsat will survive impact with the moon. This was a very sort of, the things that we did not model in this experiment is the sort of shearing that you would get if you came in at an oblique angle at the moon and got your stuff scraped off. We didn't account for that, and a lot would probably fail for that reason. But what this indicates is that maybe there's a non-zero probability of survival, and that's all we care about. It can be a tiny probability, but as long as it's non-zero, that's all that we care about. And suppose that's true, then how would you design a mission here? And so how do you think about a mission involving these things on the surface of, say, the moon? I think you could articulate mission success as being at least some number J of chipsats surviving on the surface of the body for some number M days. You figure out for whatever it is that you're trying to do, how many chipsats do I need to do it, and how long do I need for them to be alive and gathering data and communicating and so forth. And then you write down a bunch of numbers, right? So you're trying to figure out the number N, which is greater than J, that you need to deploy to the surface, subject to some probability of surviving impact and some separate probability of surviving each day. And then we'll make some simplifying assumptions. We'll assume that these probabilities don't change with time. Perhaps they in fact do. Perhaps the probability of surviving day 500 is lower than the probability of surviving day 2. But just for purposes of thinking about this, we're going to assume that those are static probabilities. And I'm going to furthermore assume that the chipsat failures are uncorrelated. If that chipsat over there failed today, I'm going to assume it gives me no information about the likelihood of that chipsat over there failing tomorrow. But then you can set this up as, just a probability equation and generate plots like the following, where we imagine on this axis is the probability of a chipsat surviving each day if it survives impact, and maybe it has a 95% chance of surviving each day, or in the upper limit, it would have a 100% chance of surviving each day. Of course it doesn't, right? But maybe it's something in that range. Against the probability of surviving impact, which is 0 down here, that is to say, every chipsat has no probability of surviving hitting the moon, up to, at the other extreme, 1, everyone's going to, and so we don't know exactly what these probabilities are, but we can make a map that describes if we deploy 100 chipsats after 100 days, if we require 5 being alive after 100 days. Assuming these ranges of probabilities, this heat map shows our likelihood of mission success. So it's a very different way of thinking about spacecraft mission assurance. This is not the way that you would generate mission survival probabilities for a conventional satellite. It's a very different way of thinking about that problem. You can also turn the problem around a little bit and you ask, assuming that we know, what am I assuming here? Assuming that we know these two probabilities, perhaps by way of experimentation, we figured these things out. The question is, what is our probability of mission success as a function of the number of chipsats deployed? What you can see is, if you deploy 800 chipsats, making these assumptions about their probabilities of survival, you have something like a 95% probability of mission success. Mission success being, again, defined as some number of chipsats survive after some number of days. And I'm just going to go through this last section quickly. At this point in my graduate work, I realized that I had been making all these claims about the utility of these things as tools for doing planetary science. And it occurred to me that I should probably do some planetary science to substantiate those claims. The easiest planet on which to conduct such experiments is Earth, obviously. And as long as I was going to be using these things to do planetary science on Earth, I wanted to be slightly strategic about this. If I'm going to be deploying these things somewhere on Earth, maybe I can find a place where I can deploy it where the information isn't just useful to me to sort of make my claims, but might also be useful to other folks. And so I ended up arriving at digital agriculture. And so I made a slightly different version of these Monarchs, one that includes, for instance, a battery, because we're on Earth, and so I don't have to survive the temperature fluctuations up in space, and that has the addition of a temperature and humidity sensor. Turns out, I was deploying these things in vineyards actually around here. The vineyard managers care a lot about temperature and humidity in the vineyard. It lets them know things like the likelihood of fungus forming or something, which can inform when they go spray fungicide and so forth. And so to make these a little bit more useful to those folks, I added that sensor and then deployed them in some vineyards. And there was something like, I tried for a while, I thought maybe this is a commercializable thing. Maybe I could make like a little company out of this. And with some help of folks at Cornell, I tried to articulate that a little bit. The essential idea being like, well, maybe there's some advantage instead of having a single weather station next to your whole farm and using the data from that weather station to inform your maintenance schedules. To make the observation that in a lot of places, Ithaca being one of them, the environmental variations over a single vineyard are pretty extreme. You can notice this actually. If you go to a lot of the vineyards, many of them are on the lake on a slope, you can feel the temperature gradient from the bottom of that slope to the top. And that difference in temperature is actually actionable. Like it actually means that you might want to treat the grapes at the bottom of the hill different than the grapes at the top of the hill. Or if you have terrain, the cool, damp air actually settles in the little divots. And you might actually want to treat those grapes differently. At present, most folks don't, right? You treat them all kind of the same. And so the thought was, well, maybe this is a tool that could facilitate more targeted maintenance. So in any case, this was my first deployment of these things over at Anthony Road Winery in Penn Yan on the other side of Seneca Lake. And this is the data that I gathered. The big dots here are the data from the conventional weather station. The little dots come from the little Monarchs right next to the vines. There's only 24 hours of data here. because you will see this big spike in relative humidity right at the end here. That's a thunderstorm that killed every board. I tried to waterproof them with like boat epoxy, did not hold up. They all died. This indicated another problem too, by the way. This was a partially cloudy day. The clouds were coming in and out of the sunshine. It was sort of sunny and cloudy. And what you could see is that when the sun was out, I was getting artificially high temperature readings. The sun was actually warming the board, right, which made for an artificially high temperature reading. So then in a subsequent deployment, put these things under little white styrofoam cups. The thought being, well, this will keep them shaded so the sun won't warm the temperature sensor. And it also protects them from direct incident flowing water, which is what really kills these things. To put these things over in Lansing with a little receiver station based on a Raspberry Pi and a little software-defined radio. These were deployed for 5 weeks. I'll show you a couple of interesting things. This I'll just mention was, I think I remember this part of my life very fondly. I would start every day at 5 a.m. by driving to the vineyard, go check all the sensors, gather the data, then come here. And it was kind of like a very nice routine. But in any case, we're looking at the data from the conventional weather station against the data from the Monarchs here. They're slightly phase offset, but it's easy to tell that like this time maps to this time. Notice a couple of things. I'm still getting artificially high temperature readings during the day. That didn't exactly solve that problem. I now know that what I needed is a Stevenson screen. It's what, if you look at, go look at outdoor temperature sensors, they're in these slat roof structures called Stevenson screens. Were I to do this again, that's the kind of device I would use to solve that problem. But we can make apples to apples comparisons at night. And there's some interesting things to observe here. At night, so this is one evening, you will observe that the Monarchs, which were tucked in the vines, like right up next to the fruit, so they're in the leaf canopy, they were measuring lower temperatures than the weather station that was out next to the vineyard. They were also measuring much higher humidity. What this indicates is that those leaf canopies are trapping cool, damp air. And what the vineyard managers care about is the environmental conditions right there next to the grapes. And so this was pretty cool. And I was suspicious of this, so I went over to the plant sciences department just to talk to them about it. And they reassured me that this is not unexpected necessarily, but it does indicate that you might actually take care of the plants a little bit differently if you are making these decisions based on the environmental conditions as measured right at the fruit. They are actually indeed different than the environmental conditions, maybe up next to the barn. Okay, I'm out of time. I also put them on some cows, baby cows. And this was mostly just to prove that we could. The thought was, let's instrument a cow, and then we'll make a version of this that's more useful for that. The only just funny thing I want to mention about this is the most interesting sensor ended up being the ambient light sensors. We didn't think that would tell us anything interesting at all. But as it turns out, these sensors would saturate low at night when it was dark, high when it was day. These little dots in the middle during the day are sleeping cows. They sleep with their chin tucked like this. And so when they were napping, they would block the ambient light sensor. And we kind of accidentally made a nap detector, which was kind of interesting. And then more recently, I've been participating in some stuff with this company SpinLaunch to try to get these things up into space. But I'll talk about that another time. If you are interested in this, there is, in fact, there's an IMAX movie playing in Syracuse called Space: The New Frontier that talks a little bit about this experiment. I'm in that movie for about 2 seconds, just long enough to go, hey, I think that's, and then I'm off the screen. So if you are interested, you could maybe go look at that. Okay, I'll be in lab in a couple hours. Have a good break. Try to take a break, and I'll see you when you get back.